Hi, can you guys hear me online okay?
Yes, we can.
Sorry, can you say that again? I don't know if I can hear you. Okay, thanks. Okay, now I can hear, I think. Okay, great. Sure. All right, so I have posted, if you didn't see my announcement, I did post the solutions in generic form along with just a example exam. So they're under the modules. So this is the modules again. And at the bottom are for exam 2 solutions and practice problems. So here you can see the fall 23. This was an example exam. There it goes. And so this would be what an example looks like. Again, they were all different. Circuits were kind of similar, but numbers were all different. So the generic solution is given underneath the solution side of that. So here's like the generic solution. All right. I had a question to kind of go over that. Do you guys want to go over? I felt it might go more efficiently if you kind of looked at it. Yes.
So using the generic solution, I plugged in my numbers and got like 118.3, and then when I did it using the same method, I got like 118.7. But when I rounded to a whole number, it was like 118. I think was the solution, and I put 119.
Mm-hmm.
Is that be like wrong?
No, you should be getting those marked correctly. If it gets marked wrong and then you've verified in the solution that, well, it really was this, you can reach out to the grader. Unfortunately, she's going to have to grade all these because I don't think the tolerance did very well this time. I was hopeful by you guys rounding to a next whole number, it would be closer. But this is one where numbers were really close and not close enough. So you'll get, you should get full credit for that. So you're all going to find, I don't know, there was no 100%. So everybody had that tolerance issue. So unfortunately, she's going to have to go through everybody's exam and figure out, you know, based on the exam, what you did. So you'll either get full credit or you'll get partial credit based on the issues of what went wrong with it. Okay. So I know this doesn't give you very good feedback for this time immediately. Some of the others gave you more feedback right away, like, yeah, I got that right or wrong. So just be patient with the grading to figure out. And in the meantime, do go over that solution, go over your solution and figure out if you did mess up, you understand where you did go wrong, so that you can do better if you can either retake it or explain to the grader what you did so that she can give you more credit if she doesn't grade you at the level you feel you should have. Yes. So Brittany Morales will be the one that will be the grader for this one. And so you can reach out to Brittany if there's any questions after she's done the grading. Do be patient. It is going to take her a little longer just because she is going to have to probably grade everyone's individually, which takes a lot longer. All right. I had a request by somebody to go over this, and I don't know. I can't remember if it was you that requested this. No. If somebody did request this, is there things that you do want me to go over with this exam? Or do you want to? I thought it might be more efficient to let you guys go over it, and then if you have questions, come on Wednesday with questions about it, particularly for that. Does that sound reasonable to do? Okay. All right, so note where that is. Again, it's under the modules. And And then you need to scroll down to that exam 2 solutions and practice problems. Okay, so that will be where the exam solution is located. And then any questions, feel free to email me if you want more specifically. Do take screenshots of your problem and your solution because everybody had a different problem. So I do need to know what yours actually specifically was with the numbers so I can look it up. Okay. So email me or we can discuss it in class on Wednesday. All right, you guys, so excited to move on, right? Okay, next material. So this is lecture 14. We are going to be covering now chapter 8, chapter 9, and chapter 13. Pretty sure it was those. Let me go back to this. Okay, and it is listed in Unit 3 in the learning materials. You can also see where it says that on the readings, it shows chapter 8, 9, and 13. So we are going to cover all 3 of these chapters. We're not going to cover them because there's 3 chapters in 1 unit. We're not going to cover the depth of it so much as a lot of breadth of it. So a lot of new terms. And the first thing we're going to cover is called complex power. So we have to understand first average and RMS values of a periodic waveform to be able to then even talk about that one. So these are the first 2 concepts is average and RMS values when you see a periodic waveform. So any periodic waveform is going to have these 2 terms in them, an average value and an RMS value. Do you guys know what those terms even mean? So average is usually what? Okay. So if you have like this waveform, what's the average of this one? Can you just look at it and say what it is? It's hard to say, right? You're like, I'm guessing. So we need to know like a little bit more accurately, like how do we find the average of a waveform such as this? And why is that useful? Because when you talk about power, never ever is power a flat line. You're always going to have some variations in power. And sometimes they're large, sometimes they're not, but you actually get also these harmonics in there. And so when you talk about power, we need to kind of talk about these concepts so that you can then apply them to things like power. But they don't always just apply to power. While we're going to apply this specifically to power, these things are also an average of any signal. Sometimes you may want to know the average of a signal so that you can take a threshold level. If you have a circuit that determines what an average is, and then you want to use that as a threshold level to then trigger some other event to happen. That would be another application you may ever come across. RMS value is called the root mean square. And that is going to be, that's a standard term that is given to you. So on a data sheet, on a power supply itself, it may have ratings on there done in root mean square. So we just have to know what those actually mean. So there's also instantaneous and average. So anybody know what it means when I talk about an instantaneous value? It's what? It's at one point. So it would be tangent to if it's a periodic waveform, it would be at that specific one time. So at one time, what is that value? Average is going to be over a time period because it's periodic. It's going to be varying over that time. That's going to be averaged. Okay. So this is the actual equation to determine what is that actual value of average. So it is taking the or integrating it over specific time t. What does t usually stand for? T always, the big T typically stands for period, which is correct in this. So this is going to be that you do need to have a periodic signal where it does repeat itself. So over one time frame of a period of that, one repetition time, you're going to integrate the signal with respect to T. The root mean square is, sorry, trying to find my notes. Sorry. Oh, I remember what I was trying to remember how I was going to describe this. Okay, so if you have a DC signal and I'm trying to find the power going on here, what is power? Is going to be the voltage across it times the current. This is I. So in this case, what is that? Okay, how did you get 20? It is 20. So this gives you 20 watts. Oh, now I lost what I was thinking. Sorry. Okay. Okay, I don't remember where I was going with this, but it's the same. Root mean square. Yeah, no, I'm not gonna get there. Okay, I'm gonna come back to the root mean square because I can't remember where I was going with this one. Okay, so applying this is what we're going to look at next. So determine the average and the RMS values of this periodic waveform. So on here, we know that the average is defined by this function. So we can use that. But we need to have it written in a function form. So how do we do that? If I was to write then this mathematically, how do I write this? I have different time periods here, right? So between 0 and 4, I can see that it's minus 12, right? So I can write this as a piecewise linear. So minus 12 between with t between 0 and 4. And then how do I write this? Okay, so I have to determine the slope. How do I get the slope? Just remember. Okay, so rise over run. So I'm using m as my slope. And the equation is usually mx plus b. Where b is your intercept that you have usually on the y-axis. So in this case, the rise goes up 12 and it goes over 4. So it has a positive slope because it's going up. So a +3. And then how do I know where it intersects the y-axis? So it would be an extrapolation over there. How do I know what that value is? So I know remember how I did this. So I know at x equals 0, I have, or it, it's, yes, so y will be 0 and x will be, yeah, thank you. Y will be 0 at, and then I know the slope, and x is going to be at 8. So this gives me that b is minus 24. So I need to plug in on this to find that intercept two values. So I know 0, whoops, 8, 0. I could do this also at x is 4 and y is minus 12, and it would also give me that b value. So 3t minus 24 is that equation. And this is between 4 and 8. And then I have another one that's going to be another slope. And you're correct, it's going to be negative 36. So 0 and the slope is going to be the same, right? You can hopefully see that. Slope is going to be the same. And then this will be 12. And so b will be a negative 36. And so this one will be 3t minus 36 between 8 and 12. And then again, it goes back to minus 12 between 12 and 16. And so and then this is going to be my period. So my period goes here. And then you can see that this repeats itself. And so that is going to be your time period from 0 to 16. And so my I average is going to be 1 over t, and in this pit click the. So your time period equals 16. And then I'm going to have to integrate each of these sections. So the first one goes from 0 to 4. The equation is minus 12. And then the next section goes from 4 to 8. And its equation is 3t minus 24. And then from 8 to 12. And then the last one is from 12 to 16 as minus 12 dt. And so this gives me, if I integrate, this minus 12 becomes minus 12t. And then I evaluate for t from 0 to 4. And then when I integrate the 3t minus 24, that becomes 3t squared divided by 2 minus 24t. And then I evaluate that from 4 to 8. And then next one is going to be 3t squared over 2 minus 36t. And evaluate it again, 8 to 12. And then again, minus 12t from 12 to 16. So minus 12, 4 minus 0. And then 3 has 8 squared. Minus 24 times 8. And then a minus 3 has 4 squared. Plus 24 times 4. And then this minus 3 has 8 squared. And then a plus 36, 8. And then this becomes a minus 9s. Good guess. Yes, you're a very good guess. Okay. RMS is going to be the square root of 1 over t, 0 to t of x squared dt. So this is the equation that we're going to use for RMS. And next time I will explain this better, like why it's this way. So for this one, we have to do the whole thing again and square root it. So square root of 1 over 16, and then each section of it. So between 0 to 4 of minus 12 dt. So you square it. And then 4 to 8, 3t minus 24 squared. Eight to 12. And that ends up giving you 9.8 amps. Okay. Questions? Yeah, 9.8 amps. Okay. You guys try one? Okay. All right. So try this one. So determine the average and the RMS value of this periodic signal. Yes.
Do you like explain what the high RMS is?
So I was trying to come up with a good way of explaining it. So
Okay.
let me think about it and then I'll come back to that.
I thought maybe I filled out for
Nope.
a second.
No, I originally had a thought of how I was going to explain it really easily. And then I'm like, I don't know where I was going with that. So I will come back to that. Some of them you'll be able to, I mean, I won't give you a super complicated one. Root something, something. Root mean square.
I can't do this with this one, like.
Okay, so I figured out where I was going with this. I was like, I knew I had this up here for a reason. Okay, so we're talking about a time varying now periodic signal that's actually input into the system instead of a DC value. So if this was periodic, it would be much harder to find the power in there, right? Because you now have like a time varying current I. And so what the RMS value is it pretty much gives you the power by if it was just an average DC input signal. So that's what the root mean square is that it is calculating it, and it's done by this root mean square. So root of x squared, and then you square root it. So root mean square. So that is where that root mean square comes from. Square root, if you don't remember that, just square root of 1 over t. You can memorize this equation or have it written down. And so what it is, again, I'll go back to that, is that with an input that's periodic, instead of having just a DC voltage there, the RMS gives you what that power would be if instead of being periodic, it was just a fixed DC value. And so it's basically saying, well, instead of it being periodic, if it was a DC value averaged, whatever that value is, that's what power I would get out of this. Okay. Does that make sense?
What is that?
So that is good for that we want to match circuits. So that gets back to this, which we want matching networks so that we have some source or some complicated circuitry. We lump it back down into a Thevenin equivalent of a VTH and a RTH. So that's your VS and RS, some source. You want to match that with a load that's going to be the most effective. And so we call this a matching network. So we want to create this matching network. And so we need to know what values those matching networks are. So now we have what's called complex power in that we match them based on maximum power output. And so with the power, you're going to have real components, which is resistors. That one we've already known, but you've never looked at, well, now we have time-dependent elements in there of capacitors and inductors. That adds in a complex matching part to it that we also have to match in the power domain or power area. And so that's why we're looking at these terms to then figure out what is this matching network going to look like.
So they take like this number and just use it straight up to match with.
So if you guys remember from like 1240, when you were matching a resistive load, you were trying to get the maximum power output of it. And so you found it was equal. Like if you had the same equal resistance, that gave you the maximum power output. And so we're going to do the same, but with the complex domain. And so we're going to now look at it in that way. That answer, does that make sense kind of why we're trying to do this? Okay. All right, great. Okay, so going back to this, so the average, well, to write the equation first, you have the slope is going to be 3/2, and so you get 1.5 t, and then it intercepts right at the 0 and 0. So you have b in this case is 0. So that's going to be between 0 and 2, and then it's 0 between 2 and 4. So when we integrate this, the average we're going to get is 1/4 is t. T is 1/4. And then, so I'm going to write that. Or t equals 4 seconds, sorry, 4 seconds. And then integrate between 0 and 2 of the 1.5 t, and then integrating 0 gives you 0 still, so you don't even have to integrate it. And then that gives you 0.75 as the average. And then the RMS, you have to take the square root of 1/t, and then square the function, which is 1.5 t squared. And then when you integrate that, that becomes t cubed over 3. And then 1.5 squared becomes 2.25. And then you do it from 2 to 0, and then that you have to square root that term, and then that's 1.225 volts or 22 volts. So your VRMS is again going to be, if this was my input and it was a periodic input, well, it doesn't make sense yet. Never mind. When we get to power, I'll say what it is. Okay. And then the average on this is 0.75. Okay. Questions? Did you guys get this? Yay. Nay. It's right here. Yes.
So even though our t is 4 seconds, we only evaluate to 2 seconds when doing the interval, because we can see that it goes to 0 after 2.
Yeah.
Okay.
Yeah. So we have to do these piecewise linearly because each section has a different equation to it.
Yeah, I was just more looking at the generic equation where it says like 1/t and then 0 to t, but
yeah.
Okay.
So because it's 0, it's going to integrate to 0.
Yeah.
So
Just
we can ignore it. Yeah, just apply it to whatever signal you have. Like in the one before, it was actually a value. So it was a shifted version. Instead of being right at 0, it's, you know, during that time period, it actually had a value of -12. So we had to integrate it there. And so in comparison to 0, it actually had a value. But it really is just a shifted kind of version, sort of that. Okay. So now that you understand those two terms, or at least understand them a little bit, and know that there's 2 equations that you have to calculate them with, We're going to move to the complex power, average power, and reactive power when we have a complex load with an input voltage and or current. So looking at this, we have the voltage in the blue and the current in the black. And the power is actually in red. So the power is going to be same voltage times current, but in this case, the voltage and current are periodic signals. And so so P of T is just going to be your V of T times I of T. So same thing, even though it's now time varying. And so V of T is this, and I of T is this. So when we multiply them, we're going to have 4 cosine 377t plus 30 degrees times 3 cosine 377t minus 30 degrees. So when you have cosine x times cosine y, this property gives you a half cosine x minus y plus a half cosine x plus y. So this is just a trigonometric property. And so in this case, the 1/2, we're going to multiply the coefficients. So 4 times 3 over 2, and then it's going to be cosine. Yes. Sorry about that. There we go. Okay, now you can see better. So 4/3 cosine x minus y. And so 377t. Well, I'll just write it out. Plus 30 degrees, and then a minus 377t minus, minus a minus 30. And then plus 4 times 3 over 2 cosine 377t plus 30, and then a plus 377t minus 30. So basically this then reduces to 6 cosine 30 plus 30 is going to be 60 degrees plus 6 cosine 2 times 377t. And then those will cancel, 30 minus 30. So this would be our power. And graphically, it looks like the red power up there. So now the averaging of this power is going to be that same equation, is the periodicity. So 1 over that time t period, and then 0 to t of p of t of dt. So generically, this is going to be your voltage amplitude This is going to be your current amplitude. And now we have a new term. The subtraction of angle is going to be a power factor angle. And that will be used here too. And then this actually ends up giving us 0. So a cosine, when you integrate it, has the same on the top and the bottom, and so it ends up being 0. And so over this is going to just be some number. And so we don't have to actually integrate it. All we have to do is use this formula. So amplitudes of both divided by 2 times the cosine of the angle differences between the voltage and the current. Oh, sorry. Give you a second here. Okay, so our talk of complex numbers, we've used the term just S so far. So now we're also going to talk more about S can be equal to J omega. And so if we're looking at, well, okay, S equals J omega, I'll just leave it there. And then these are properties of complex numbers. So you have the rectangular form. And what was this term again out in front of the E? It's the polar form, and that number in particular is called the magnitude. Thank you. So this is the magnitude, and then you have the angle in polar form. Angle. And then the real component this is the real component, and this is your imaginary component. So those are kind of the terms you need to remember from complex numbers that we've already kind of gone over. There's thing do we need to know here? Okay, so this is a little different perspective on resistors, capacitors, and inductors. So in the circuit, a resistor only has a real value. So it's going to only have a phasor going in the real direction. So that's why you have just see that the current and the resistance are going both in the real direction. For a capacitor, we had 1 over CS, and your voltage and your current is equal to your voltage divided by 1 over CS. So it ends up being VCS. And then if we look at S as J omega, to bring in that J, it becomes the J omega C times the voltage, VC. And so in comparison to that, what does this J do to your angle? It's going to be J is also equal to EJ90, right? Or it's written here, it's easier. So the current is equal to voltage is in the positive direction because it doesn't have any complex portion of it. It's just periodic. And so you have now this J, so you get I is going up by 90 degrees. Right? So J can be written as EJ90. I will write that. And similarly with inductance, this becomes LS. And so current is going to be VL divided by LS. And then plug in J omega for S, and that becomes J omega L, which can also be written as a minus J VL over omega L. And in this case, you get 1 over J is equal to minus J, or you can say it's E to the minus 90 degrees. So your current goes down and your voltage is still in the real direction. So now you can see how this is shifting by component only. It's shifting your current based on your input by 90 degrees for a capacitor, by minus 90 degrees for an inductor. It's just telling you that in comparison to your voltage, your current's going to be shifted from that either minus 90 degrees or positive 90 degrees. Correct. It's just the shifting in comparison to itself. But that shift gives us information about the average power of it. And that's why we're looking at this.
That's like just another different time.
So if my input was, say, like cosine of something t and no shift at all to it, and that's my input voltage, if I have a capacitor in that circuit, that each capacitor is going to shift it. So the current, when I look at it in comparison to that, is going to shift it by positive 90 degrees from that first one. So if I'm looking at a cosine, it's just going to shift it that value minus or plus 90 degrees.
Okay.
And then the inductor will do the opposite. It will be cosine, whatever, 12t minus 90 degrees. So it just shifts it in comparison to the other input. Okay. So, so if you guys remember from 1240, you guys did phasors. And phasor solution is for one frequency value. So we just did Laplace. It was not limited to one frequency value. It could be any frequency input. It could be any complex portion of a input. And so that was the strength of the Laplace. We weren't limited, which phasors are limited to one specific value. What we're going to look at for phasors is it's usually easier solution to get to, though. And we're going to look at it in the power to get the component values we want. And so that's why we're going to use this technique. So if you remember from phasors, transferring to the phasor domain, you have to do it in J omega form. So that omega will be the one frequency of your input. And the input is going to be determining the frequency. So frequency never changes. You have to put the input, though, into a cosine form. So if it's sinusoidal, you have to move it to a cosine with some shifts of something. Or it could be addition of a whole bunch of cosines. But you have to be in cosine form to use phasors. And then from there, you use the frequency to determine your ZL, your inductance impedance. And that was just J omega L. So remember, S is equal to J omega. So it looks very similar to the Laplace. And you just put in that value for omega. So sine omega t minus 45 degrees. How do we shift that to cosine? Yep. So cosine omega t you do minus 90 degrees from cosine. So this would be minus 90 to change it from sine to cosine, and then add the minus 45 degrees again. So that gives us minus 135 degrees. And then you put it in phasor form, so it becomes 12, which is the amplitude e to the minus j 135 degrees from that shift. So remember, it was the amplitude and then the phase shift from your input signal. And then you use the omega, which is the same omega as your input, to determine the J omega C value for the capacitor. If you have an inductor in there, it's just J omega L. And so you change it into that phasor domain, and then you use the whatever equation set. You can use node voltage, you can do any other techniques. You get your equations, and then from there, you then transfer it back into the time domain using the omega from the original omega. And once you get it into phasor form, then you take the real value becomes your amplitude, and the angle becomes the shift of that angle. Do you guys remember this? Sort of remember? Okay. So now how does complex power kind of come into this? So complex power, we have, again, some more terms. So apparent power is going to be the magnitude of the power, and it's going to be the multiplication of just your RMS values from the voltage and your RMS values from the current. So that's why we went over that exercise. They're going to be periodic equations, and we just want the average of each of those. You multiply them together, that gives you the magnitude of the complex power, which is another term is called apparent power. We then also have this power factor, which is going to be the cosine form of the shifts in the angle from the voltage minus the angle in the current. Depending on how that power factor, it's going to tell you if you only have a resistive network, if it's 1. If it is less than 90 degrees, you're going to consider it lagging, meaning it's an inductor, right? It's an inductance because it's lagging behind minus 90. Or sorry, no, it's, yeah, inductive, but it's not minus 90. It's between 0 and 90, and it will be leading, meaning current leads the voltage if it's negative. So it's a capacitive if it's a negative value. So here we have now our load is going to be both resistance and some inductor capacitance combinations, which is going to be the imaginary part of it. All right, so complex power is the average power plus this JQ. So it's going to be, this is rectangular form. The average absorbed power is the real part of this, and the reactive power is the imaginary portion of this. So in terms of complex power, we want to get this in rectangular form. And you're going to love this too. So new units. We have volt ampere, VAR, volt ampere reactive, and average power is going to be in watts. That one we know. The other two are new. So you get new terms. And then when if you ever work on power systems, you're going to start to see like volt amperes and volt ampere reactive, VAR and VA. All right, so the next thing we need to do is calculate these values. So how do we do this? So you're given a voltage signal and a current signal. Sorry, lost my notes for a minute. Okay, so let's do A. So for A, we want to find the complex power. And so we're going to take volt RMS, and then we take, go back to this. And then we take IRMS. So how do we find this? So all we need to do is change these to polar forms. So what will be the polar form for the voltage?
And
Correct. So you're going to take the magnitude and then you just take the angle. So this is the phasor form of that. So what will I be? Correct. Right. So now from here, the VRMS is just going to be um, 1 over the square root of 2 times that. And then IRMS is going to be the same, 1 over the square root of 2. So now when we take the S and we just multiply these together, 1 over the square root of 2, 110. 1 over the square root of 2, 4. And then minus 60, minus 25, J. Oh, this was missing. It's the complex conjugate of IRMS. So this will be a plus 25. Mark that. And so this ends up being S is 220. E to the minus J 35 degrees. And this is the volt ampere. So that unit is volt ampere.
is S different than the S that was even average plus JQ? Or that's
I don't know. This should be a complex conjugate. Oh, there it is right here. I was like, okay.
But if you scroll up just a smooth. That S right there, the P added to the P,
Uh-huh.
is that,
So that's in rectangular form.
okay,
Now we have it in polar form. We can change it over to rectangular form and then get those two terms. So VRMS is really nice in that if you have it into polar form, all you have to do is take 1 over the square root of 2. So you don't have to do the whole thing again, like the whole integration again. So that integration average for the RMS and the square root of that average is just 1 over the square root of 2 when you have it in the polar form. And then it's just multiplied by that number 110. Yes. So remember RMS, let me go back to this. Where did it go? This is RMS, is you take 1 over the period. And in this case, we have a cosine. And so when you do cosine squared and you take the average of that, or you take the integral of a cosine, it ends up being 1 over the square root of 2 for that, because the period is just the same. So that all ends up just being 1 over the square root of 2 times the polar form. So yeah, just 1 over the square root of 2 was resultant from that. And then, so this gives you complex power. And now we want to get the apparent power. What was the apparent power? So that's the real part of this, right? So this is in polar form. So we just change it over to rectangular form now. So how do we change to rectangular form? Let's remember that. So you take the magnitude and then cosine of the angle. That will give you the real portion. And then the magnitude times sine of the angle gives you the imaginary portion. And so this ends up giving you 180.2 minus 126.2 J. And so P average, which is the apparent power, is just 180.2, and that's in watts. And then the average power absorbed is, let's see. Oh, sorry, that's not apparent power. That's the average power absorbed. This one. And then the reactive power is going to be the Q. And that's going to be the minus 126.2. And this one is in volts active reactive, or volts ampere reactive, VAR. The apparent power, sorry, let me go back. The apparent power is just going to be the magnitude. I'll straight here. Apparent power is the magnitude of S. And so in this case, it's just 220. S is volts ampere. And so the magnitude will also be in volts ampere. Okay, so then PF, the power factor, and then determine if it's leading or lagging. So PF is going to be the P average divided by the apparent power. And so that will be 180.2 divided by 220, which gives 0.819. And so that is going to be leading. So on this one, it's the angle of V minus the angle of I. And so the angle of V was minus 60. And the angle of I is minus 25. So you get a minus 35 degrees. So in this one, a minus 35 fits here, so it's leading. So that's where the leading came in. So this is determined by this value. All right. So going back, equations you need to know, this PF equation. This term, which is going to be the real portion of S, the reactive power term, which is the imaginary of S, the apparent power is the magnitude of S in polar form. So understanding those terms, getting the S in polar form. So this is your complex power. And then how to determine volt RMS and I RMS. So if they're in cosine form, you can find that by just taking the 1 over the square root of 2 in polar of those. If they're not in polar, you have to transfer them over into polar form. All right, any questions? Okay, we're gonna do more next time. Any questions online? All right, see you guys.